Thank you for attending this session. The topic of this session is Materialized column, an efficient way to optimize queries on nested columns. Firstly, let me introduce myself and our team. My name is Guojun, and my English name is Jason. You can call me Jason. I'm the lead of data engine team at Bytedance. We are the data engine team of Bytedance. We build a platform of one-stop experience for OLAP queries and also for ETL pipelines, on which users can analyze PB-level data by writing SQLs without caring about the underlying execution engines. And what do we do? We manage Spark SQL and Presto and Hive workloads. And we offer open API and self-serve BI platform. Also, we optimize Spark SQL, Presto, and Hive engines. Actually, we are the maintainers of these big data engines in Bytedance. Besides, we design data architecture for most business lines in Bytedance. Here is the agenda. Firstly, I will introduce the Spark SQL at Bytedance, followed by why nested type are widely used in Bytedance. Then I will explain what are the main issues of nested type, followed by the optional solutions. Lastly, I will illustrate how does materialized column solve these problems. Let's go to the first part, Spark SQL at Bytedance. We adopted the Spark SQL in 2016, and at that time, the Spark SQL, we just used Spark SQL in small-scale experiments. 1 year later, in 2017, Spark SQL mainly supported the ad hoc workload. And then in 2018, we use Spark SQL in a few ETL pipelines in production. Later, in the 2019, Spark SQL support both ad hoc queries and also ETL pipelines. Now, in 2020, Spark SQL is the main engines, big data engines in data warehouse area in Bytedance. Now, more than 98% ETL pipelines are running on top of Spark SQL, and almost all the new created ETL pipelines are created based on Spark SQL. So we say that Spark SQL is the main big data engine in data warehouse area in Bytedance. Okay. Let me explain why nested type are widely used in Bytedance. There are many two types of data in Bytedance. The first part, also the largest part, is the event log. Event log. By event log, we mean that, for example, we may store some tracking events in event log. Also, we may store the user action and the server impression, and also the client impression data in the event log. Let's take the event log. Let's take the tracking events as an example. A lot of new tracking events are created every day, and for each type of event log, there are many subfields, a few fields or tens of subfields for each type of event log. If we store all the subfields in a separate columns, there are maybe millions of columns in each Hive table. I think it's not a good idea for us to set up millions of columns for a Hive table. And also, even though we can store all the columns there, but it's not a good idea to create new columns and remove existing columns frequently, because maybe today we add a new type of tracking event. We need to add some new columns. And tomorrow we may remove some existing tracking events. So we need to remove these columns accordingly. So it's not a good idea to create a new column for each of subfields of each event log of each event. So indeed, we just set up two columns. The first column, the name is event type. So we just put the event type there. The type is string. And another column, the name is message, and the type is map. We just put all the subfields in a map, and then we put the map in the column. So we only need two columns for this tracking events. And that's why we need to introduce the map type, the nested type, to our Hub table. And for another type of data, we call it dimension data. The dimension tables are dumped from MySQL. The MySQL is serving the backend service. And for the backend service, they may add some new fields on demand, or they may remove some fields. If we do the column addition and the column removal in the Hive table, it's not a good idea, because for Hive, we should not remove the columns, because in the Hive, we need to store all the historical data. When we remove the column, it may occur. There may be some message loss. And for some new added columns, I mean the new added fields, it may be not very useful for now, but they may be helpful in the future. So we also need to store these fields, these subfields. So indeed, we may store some frequently used column, the fields, in a separate column, and then we put all the other subfields in a JSON string or in a map. Okay, let me explain what's the main issues for these nested types. Let us take a look at the picture on the right side. In the picture, let us take a look at the bottom. In the bottom, there is a table named a base table in red. The base table contains 3 columns. The first column, the name is item, and the type is string. And the second column, the name is count, and the type is int. But for the third column, the name is people, and the type is map. We know that the map will contain the data in a key-value pair. And in the picture, we can see that there are 3 keys: the name, age, and gender. In this session, we will refer these keys as subfield. So in the column of people, there are 3 subfields: name, age, and gender. And on the top of the picture, we can see that the user issue a SQL. The SQL may be like this: select people, appoint age from base table. So the user only want to pick out the age from the people of the table. But the Spark SQL have to read out the whole column of people. So the Spark SQL have to read out the whole map. But only one of the subfields, the age, is the only one that user want to read. But the whole map is read by Spark SQL. In our production, the map may contain hundreds of or even thousands of keys, thousands of subfields. But each time, only a few of the subfields are needed. But Spark SQL have to read out hundreds of or even thousands of subfields. So the first drawback of the nested type is that Spark SQL may read many unnecessary subfields, which is a waste of I/O. Now, the second drawback of the nested type is that in Spark SQL, when we read the Parquet data, Spark SQL provide a vectorized reader for Parquet, but the vectorized reader for Parquet can only read the atomic types. In other words, if the Spark SQL need to read some data from a nested type, vectorized reader will not be used. Instead, the Parquet ML will be used, which will read the data in tuple at a time way. So the vectorized reader cannot be used for nested type. Okay, let's go to the third item. Each time when a nested type is read, filter pushdown cannot be utilized because the filter pushdown, the mechanism for the filter pushdown is that the reader will read the min-max index before they read the actual data. So, but for the nested type, for the map type, the Parquet cannot build the min-max for each subfield of the map. So the filter pushdown cannot be used when nested column is read. Besides the map, sometimes we may use JSON, and the JSON parsing is CPU intensive, especially when the JSON string is very long. For example, when we store hundreds of even thousands of subfields in the JSON string, and when we try to parse a few fields from the JSON, is not efficient. For these four issues, we may have we design some optional solutions. Let's introduce two of them. The first optional solution is that we can create a separate table. For example, on the right side, we can see there, besides the base table, user can create another table named subtable. We can see in the picture that the subtable have another column named age, and the age the content of the age is the same of the subfield age in the people column. Actually, in Bytedance, some users tried these solutions, but for this solution, there are some drawbacks. Firstly, we need to push all the downstream users to migrate their queries or pipelines to the new table and the new columns. But sometimes it may be impossible because there are tens of or even thousands of downstream users. So it's not easy for us to push them to migrate their jobs to the new table or new columns. And there will be some duplicated storage and computation costs because we need to maintain two tables. And also, this solution cannot handle the frequent subfield changing because today the subfield of age is frequently used, and tomorrow maybe the age is not used, and the name will be used frequently. So we need to change the column. We need to remove the age column, and we need to add the name column. And it's not a good idea to frequently remove columns or add some new columns. And also, we design another solution. We refactor the Parquet vectorized reader to support vectorized read for nested types. And we try to support predicate pushdown for struct, only for struct, not for the array and the map. This solution enables vectorized read without any storage overhead. And indeed, we improve the performance with struct by about 100%. And also, we improve the performance with map by about 163%. But there are some problems. Firstly, we need to refactor vectorize the reader for Parquet and ORC respectively. And also, filter pushdown for array and map is still not available. And the performance of vectorized rate on nested type is not as good as that for simple type. So we designed the materialized column to solve all the problems. On the left side, we can say that we create a table, the original table. We create a base table and item count and people and date. The date is a partition column. On the right side, we just alter the table and add some materialized column. We can say that alter table, base table, add columns. Age. The age column is added, and we use some keyword materialized, followed by expression cast people age as integer. Let us take a look at the right side of this picture. We found that we just add a new column. The name is age, but we set some mapping that we know that the age is from the people point age, and when user try to pick out the age from the people, they just write some SQL, select people point age from base table, and the Spark SQL will rewrite the SQL into select age from base table, and this SQL rewrite is done by Spark SQL automatically. So now the new SQL is that select age from base table. So we do not need to read out the whole people, the whole map column into memory. Instead, the Spark SQL only need to read out the age column. The age is in integer type, so we can use the vectorized read, and also we can use the filter pushdown. So the performance is improved. Let's take a look at how we design and implement the materialized column. Here, in this slides, we just insert a tuple into the table. We explain the SQL, explain extended, insert into base table, and select apple. The apple is an item name, and one is a count, and a map. The map is for the people column. So we can say that we only need to insert 3 columns, and we do not need to care about the new added materialized column. We do not need to insert the age column in the SQL. So each time when we add some new materialized column, the pipelines do not need to change. And on the bottom, we can say that after Spark SQL optimizes the SQLs, we can see that the age column is added automatically. So the age column is provisioned automatically. Okay. Let's take a look at these 2 pictures. On the left side, we can say that the left picture shows how the execution plan for the SQL without a materialized column rewrite. We just extended select cast people age as int, and from base table. Without the materialized column rewrite, we found that Spark SQL need to read out the people. The people is in map type. The Spark SQL need to read out the whole map, and then Spark SQL will extract the age from the map. But let us take a look on the right side. We found that Spark SQL only read out the age column. The age is in integer type. So from the data screen, the Spark SQL only read out a single tab, the age column, and after the SQL analyze, we found that the project in the middle of this picture, we found that Spark SQL only select the age column from the table. Okay, lastly, let me explain how the materialized column improves the performance. There are three use cases. Let's take us at the first test case. We found that without materialized column write, the end-to-end time latency is 6.3 minutes, and about 800 gigabytes are read. But when we enable the materialized column write, the end-to-end latency is about 3.4 minutes, and only 100 gigabytes are read. So the end-to-end performance is improved by about 85%, and we reduce the read data size by 86%. Okay, thank you. This is all for this session.